Morning, everyone. So yesterday we ended off with looking at limiting excess. Basically, the idea is if I give you information for more than one chemical, there's a good chance that one chemical might run out first. The second that one chemical, called the limiting, runs out, it limits the overall production and basically stops the reaction. We saw that all our calculations so far have been what are called theoretical yield. So in a perfect world, those should be the maximum amounts that you form. But normally when we do a lab, due to a whole host of errors, usually our actual yield, the actual amount that we form, is even less than what we calculate. So I'm going to give you a quick question on calculating similar to a percent yield, but I'm going to frame it as a percent purity. And after we go over this question here, we'll look over titration as a technique. So just as a warm-up here, this question here we worded here, calculate the percentage or percent purity of an impure zinc block if a 3-gram sample forms 975 milliliters of hydrogen gas at STP. And I'll give you a corresponding equation here. So we have zinc. The reaction is actually dropping zinc into hydrochloric acid. It's a known property for metals that they do react with acids. So single replacement reaction here, we're going to get zinc bonded with chlorine. You double check your compound, should be ZnCl2. When hydrogen gets kicked out by itself, it's one of those diatomics. We do want to make sure that our equations are balanced before you do any other stoichiometry. So as always, I like starting off with a picture if we can. So currently they give you 3 grams, and they're just implying to you that this 3 grams here is impure. We were labeling it as zinc, but probably it's been embedded by a whole bunch of other chemicals here. We're going to be under the impression that it's only the real zinc here that actually reacts with the acid. We're just going to assume that these impurities here don't react in the same way. What we're told is we actually form 975 milliliters of hydrogen gas here. Hydrogen's over here, so I can just put 975 milliliters. So there's 2 main ways of doing this question here. You can do it like a percent purity question. You can say, well, let's pretend if I really had 3 grams of zinc, how much true volume of H2 should I have gotten? And then I can do a ratio. Well, by calculation, I should have gotten something over 975. 975 divided by that number is percent purity. Another way of doing it here, just sort of introducing to you the framing of percent purity, is actually working backwards. This guy here is sort of like your actual yield, because they actually tell me this is how much formed. In a perfect world, how much zinc would I actually need to form exactly 975? I can actually do a calculation back over. Let's figure out how many grams of zinc are there actually in my 3-gram sample. And then by doing a fraction there, just like I would over here, we call it percent yield when it's on the product side, but we'll call it a percent purity when it's on the reactant side. So because we haven't done it the second way, I'm going to show you this way here. How many grams of zinc do I actually have, given that we start off with 975? Usually, if it's milliliters, I just convert right to liters, because whether we're using 22.7 or concentration, we'll need liters right away. So either just move the decimal place by 3, or you can show it in that fashion. Because we are a gas at STP, we can assume here for every 22.7, that's the molar volume. We calculated from ideal gas law. And our stoichiometry allows us to do, well, based on the mole ratio, for every 1 part H2, it's 1 part zinc. Because later on I'm going to compare it to grams of zinc, I'm also going to be multiplying here the molar mass of zinc here. I'm getting here 1 mole, I believe it's 65.35 grams. So numbers on top you multiply, on the bottom you divide. We'll see what we get here. Don't bother typing any times ones or divide by ones. I get, based on 3 sig figs here, 2.81 grams, right? So sort of we're under the second interpretation. If we really produce 975 milliliters, I would need 2.81 grams that's actually zinc. Well, actually my sample was 3 grams. Shouldn't be that hard for you to calculate a percentage then. Well, if 2.81 is the actual zinc that's there, and I have a 3-gram sample that's impure, the units will cancel out, grams cancels grams, and then we'll figure out here if you can keep the whole number and calculate it even better. And I get here 93.6% as the purity. If you had done it the first way here, you could have started with 3 grams instead. You could have used some of these same conversions, molar mass, molar volume, whatnot. You would have got something over 975. And if you did that ratio 975 divided by that number, you'd also equivalently find it's 93.6%. So usually just, it's called percent yield. When you're looking on the right-hand side, if it's on the products, it can be framed as a percent purity question. But in both cases here, they're just saying, how much real zinc did I have to form the actual hydrogen, assuming the impurities don't react in the same way. All right, so for today's lesson, I'm just going to introduce to you a very common technique known as a titration. This titration here, the whole goal of doing a titration is to find an unknown concentration. And so far, the solutions that we talked about here have been like solids dissolved in liquids here. Imagine you start off here with the bottle. This is maybe my stock bottle here, and this bottle here will be labeled here, I don't know the molarity of HCl. So here's a chemical that I know the chemical, right? I know it's HCl, I know it's hydrochloric acid, but I just don't know how concentrated it is. I don't know if it's really strong, like 12 molar. I don't know if it's previously been diluted with a lot of water. What we're going to do is we're going to use this technique of titration in order to find this concentration, and then you can, once you know that concentration, use that for future experiments. How titration works here is we're actually going to run this through a reaction. So seeing as our unknown in this example here is HCl, I'm going to run it through a reaction with the acid-base neutralization. So let's run HCl. Let's purposely react with NaOH. In some sense, as we're going to walk through the experiment here, we're going to be using our NaOH to count how many HCl particles there are. We know in the acid-base neutralization here, this will form a salt. So this is actually table salt, NaCl, and we'll end up with water. As always, we want to make sure that everything is balanced so that we can do our stoichiometry. All right, so here's our typical setup for our titration. We're going to have one of these chemicals, right? And I'm going to be neutralizing a base and an acid here. One of the chemicals goes in the burette. Just a reminder here for a burette, for some reason here, the 0 mark is up here. The 50 ml mark is down here. Let's fill this burette here something over half. Okay, so I'm just going to fill it up there. Let's say we happen to be at the 10.00 mark. That's what this initial reading says. Be careful though, this 10 milliliters doesn't mean that there's actually 10 milliliters in the burette, because if 50 is down there, 10 to 50 is already going to be 40 mils. But the whole way of reading a burette here is we're going to take a starting reading, we call that V initial. After we open and close the stopcock valve here, we dispense the NaOH here into the bottom solution. The bottom solution is actually where our acid is going to be. Overall, the volume would have dropped. We just take another reading on the burette here, and we just see, well, what does it say later on? Totally make up a number here. Let's say 31.20 milliliters. That also doesn't mean, oh, there's actually 31 inside the burette. What I'm going to do instead is I'm just going to take the difference. That difference there will actually be how much volume I actually dropped in. So in this case here, it doesn't really matter which one you put in where, but in this example, I'm just going to put, let's say the base goes in the burette. That way we can drop the base. We have our base here. Although we do have an unknown concentration of HCl, the other chemical, I have to know the concentration. So we'll talk about that some more in just a second here. Let's say our NaOH concentration here is a known value. Let's say the concentration is 0.500 molar. The whole point of doing a titration, like I mentioned, is to use my NaOH. Let's count how much HCl there is, and then I can sort of back calculate, well, how strong the acid itself was. Now, I know I have a big vat of this acid over here. I don't need to destroy the whole sample in my titration. In fact, because concentration is an intensive quantity, what if I just poured a little bit of that to actually test? Usually what we do is we use a smaller glass instrument here called a pipette. We withdraw. Our pipettes usually come in 10 mils or 25 mil portions here. Let's say I pour a 10 milliliter portion into this bottom Erlenmeyer flask here. This one here so far is unknown concentration HCl. It may be really, really concentrated, meaning there's going to be lots of H+, lots of HCl around. It may be not very concentrated, really dilute, maybe only has the odd few H+. At this moment, I don't know, but I've decided to use 10 milliliters to do my test. All right, so as I mentioned here, how we're going to do it, we're going to slowly drop in the NaOH, and what we're doing is, again, we're using the NaOH to slowly count the acid for us here. So I have some unknown amount of H+, so far I've drawn 3 particles. Let's just steadily, we took the reading at the beginning, let's just steadily open the stopcock valve. As you open the stopcock valve here, you're going to slowly drop in the NaOH. As the base here enters your Erlenmeyer flask, as long as the base particle can find acid particle, overall your solution is still going to be acidic. Now, one other sort of little cheat here is, unfortunately, both the HCl and NaOH are colorless solutions. Sure, hypothetically, yeah, I know the HCl is supposed to be killed off by the NaOH particle. It's all in a 1-to-1 ratio. All that stoichiometry is good. I would have no idea whether is it still overall acid like my picture shows, or have I killed off all the acid and now it's actually base. What I'm going to do is I'm going to throw in a little cheat here. That cheat here is going to be called an phenolphthalein. Phenolphthalein is an example of an indicator. And for an indicator, all we really need to know is this indicator here. If we are overly acidic, it's going to be color number 1. If we are in a basic solution, we're going to be color number 2. Next year, we're going to do a whole chapter on acid bases here. We're going to see a whole bunch of indicators. They all have different pHs where they actually change color. For phenolphthalein here, what I'm going to tell you, for the acid, it actually stays colorless. So even colorless can be color number 1. As you become overly basic, it's going to switch to a very deep pink color here. And here's what's going to happen here. Before you're ready for your titration, I'm going to drop in a few drops of phenolphthalein. Right? Just a couple is there. It just needs to be present. At first, it's overall H+. It's overall acidic. The phenolphthalein is going to stay colorless. As you steadily drop in more and more OH-, at first, when there is the presence of OH-, the phenolphthalein will already start turning to a pink color. But as you swirl this Erlenmeyer around a little bit more, as the OH- here runs to H+, as long as we are still overall acidic, even if it temporarily showed pink color, it's going to remain colorless. However, as we get closer and closer to what's called the end point, or the equivalence point here, when this reaction here is perfectly canceled out, I have perfectly good count on how much HCl there is, we're going to see there's steadily less and less H+. As you drop in your hydroxide, that pink color that your phenolphthalein show is going to stay longer and longer. What we are looking for here is called the equivalence point. Equivalence point is basically the stoichiometry point where I have just perfectly added in the right amount of base to kill off the acid. So equivalence point here is called when the moles of H+ is equal to the moles of OH-. I've dropped in just the right amount of NaOH to count how much acid there is. So at this point here, OH- is killed off H+. Again, remember at this point here, I have no clue how concentrated it is. All I know is if the concentration was really low to begin with, it's not going to take much base and I would already hit this equivalence point. If it is much more concentrated than I'm thinking, you're going to run through a lot of this solution of bread before I end up hitting this equivalence point. The only difference is how much volume do I drop in until I hit this equivalence point. At the equivalence point here, imagine dropping in one extra drop of hydroxide. Now the hydroxide from the NaOH here, it can't find any more acid left. It can't neutralize with it. And therefore, the phenolphthalein that has always been in the background, suddenly it notices that we're fully in a basic solution. Suddenly, it's going to switch to a pink color. And in this case here, we call this color change point here, we call it the end point. Basically, when that pink color first switches over and that pink color stays, I know to stop. Basically, I don't want to have any limiting excess. I don't want to accidentally, very common in titration technique here, whoops, I opened the burette too much. I dropped in way too much NaOH. Sure, the phenolphthalein turns way pink. But unfortunately, there I would have so much hydroxide in the solution here. I would have so much excess NaOH, and then, therefore, I won't have a good count on how much HCl there is. I want to have dropped it in exactly, slow enough, that I hit perfectly this equivalence point. Then I can just do stoichiometry between these two ratios here. So let me just demonstrate to you how this data would typically look like. In this case here, I'm dropping in base. Again, you would note down here, maybe in a table, the initial volume reading from your burette. Usually you do a couple titrations, so a couple trials. And what you're going to record down everything from the burette. So first trial is usually let me just get a ballpark. Let me get a sense of how acidic it is. I'm just going to do this here. So 10.00. We're going to find burettes can be read to 2 decimal places, so 0.05. So far, let's say I open and close a burette. I toss in the hydroxide. Turns pink, it doesn't stay pink. Turns pink, doesn't stay pink. And you keep tossing it in until you hit that endpoint. Oh, now it looks like the pink color has just started appearing. I know I want to stop at that point. So this is now your final volume. So far from what I've given you here, let's say it was 31.20. Let's say I wasn't as confident in that reading. Let's say 0.06. Remember, you as the experimenter have the ability to decide how big that error is going to be. What we're interested in, again, is the difference in volume. Again, I want to remind you, it's by taking big number minus small number, that's actually how much I've actually added. Based on my numbers here, it would be 21.20. Errors end up adding, so it's going to be 0.11. We always want to round it if we can, so 21.2 plus or minus 0.1, and that way your error is only 1 sig fig. So that there is the volume of NaOH that I dropped in when this pink color showed up. Then what we do in science here is we do another trial, right? I just want to make sure that this wasn't by fluke that this happened here. I'm noticing it's taking some 20 mils or so. My burette is going to empty at 50. So between 31 and 50, there's not quite 20. What I would do then is I would just refill my burette. Usually I just tell people, usually something more than half, so that we have enough titrant volume. We have enough volume in the burette to perfectly get to the equivalence point without having to refill mid-trial. Because every time you refill, there's going to be accumulating some random errors. So I'm noticing here, oh, I don't have enough in my burette here. What I'm going to do is I'm going to refill my burette. Let's say the next time I refill my burette, let's say I actually get it up to this top volume here. Let's say for argument's sake here, it's at 5.23. I don't really care what the starting volume is because I'm just going to take down what that reading is going to be. And then what I'm going to do here is I'm going to run through my titration, right? I reloaded it before I did my titration. I'm guaranteeing I should have something about 20, right? I'm doing another trial. Maybe it's going to be somewhere close to that there. And let's run through the titration. So have a fresh sample of HCl. You reloaded your burette. You took down a starting reading. That was the 5.23. You open and close the stopcock until this pink color appears again. And this happens at 26.53 plus or minus 0.05. Again, it's the difference in volume that we care about, just to make sure that these are consistent. You do the subtraction, and this one gives me 21.30 plus or minus 0.10. Again, we would round it 21.3 plus or minus 0.1. Right? Even with that, that's actually have a lot of confidence because between one trial and another trial, these volumes that overall dropped in for NaOH here are fairly close. These guys here are called titrant volume. So this is how much volume I use. The titrant in this case here is the base that I'm dropping in. Because I know the endpoint happens in about 20 mils or so, I would have enough, right? Remember, I have down to 50. If I add 21 to 26, that's only about 48, 49. It might be pushing it, but let's just give it a go. So let's keep the burette reading here. I just finished my trial here. It was reading 26.53, and now I start my third trial with that beginning reading, right? 26.53, let's say 0.05, 26.53. You run through your titration here, and you try to figure out when does this endpoint get reached. And it says here 48.04 plus or minus 0.06. Doesn't really matter. Again, you always, for the burette, you always take these two readings. It's the difference that we overall care about. So let's go 48.04 minus 26.53. This one gives me here 21.51 plus or minus 0.11. Again, round your error to 1 sig fig, and then make sure it lines up. I'm getting 21.5 plus or minus 0.1. So what I've done here is tested 3 separate samples. I did the titration through 3 times. I'm expecting these 3 here to be fairly close, which they are. At this point here, depending on how your numbers look like, you have to use your judgment. If all 3 numbers are sort of really different from each other here, I'd average all 3. In this case here, you're noticing, hey, my first 2 trials are a lot closer to each other than this third trial. If you're noticing one is far off the other one, you can say this one here is an outlier. Maybe I overshot the endpoint. Maybe I went too far. Maybe I added way too much base, a little bit too far as compared to the other one. Maybe I've overshot that, and I can totally ignore that one. Take the 2 close trials here, make an average. So let's do what is the average NaOH that I dropped in. 21.2 plus or minus 21.3 divided by 2. And then the errors also get average. Right, that's my error there. This is going to be 21.25 plus or minus 0.1. And then I just round it again. So 21.3 plus or minus 0.1. Right? So just to show you, sometimes if one of them is overshot, you as an experimenter, you can just drop that out. At this point, believe it or not, it just falls down to a stoichiometry problem. So because I already knew my equation, it's HCl reacting with NaOH, becoming NaCl and H2O. Let's make a list of what I know. So the volume of the base is 21.3 plus or minus 0.1 milliliters. Remember I told you for titration, one of them you have to know the concentration. The concentration of NaOH here was given to me as 0.5. So this one here is going to be 0.500 molar. I didn't know the concentration of acid. That's why I'm interested in finding. In fact, sometimes they even give you a ballpark. I know about what it is, but by doing this titration here is to give you a little more precision. As you have dispensed in extra 20 milliliters, at first we were only 20 milliliters, we'd probably be about 30 or so milliliters. It's sort of just an unfortunate fact that this volume here actually ended up being higher. We know, however, once you have a good count on the H+, all those moles of H+ here were initially just sitting in 10 milliliters. So even though I've completely destroyed the sample, I'm just going to take the moles of H+ that I found, divided by the initial volume that I pulled from the acid. Taking that ratio will give you the concentration, and that concentration will apply to the entire bottle. So even though overall your final volume, let's make an error on the pipette here, let's say 0.04. Note that this one here is the initial volume. It's the starting volume that your acid started in. Remember, I did this slow enough that there's no linear excess. So basically, every single base particle is counted however many acid particles there are, and I just do that ratio and I get my concentration. So let's try it out here. I want to find the concentration of HCl. I'm going to start off with the one that I know more information, which is the NaOH and the 0.5 molar here. I'm going to convert this one here to liters, so 0.0213 plus or minus 0.0001. So that is my volume of NaOH. I'm going to use concentration to get it over to moles, so 0.500 moles for a given liter. I'm going to use the mole ratio. Sometimes it is not 1:1, so you have to use a balance equation. In this case, it is. For every 1 mole of NaOH, there is 1 mole of HCl. And in this case here, it's going to feel a little bit weird in terms of how we're setting up our work. We're used to doing top unit cancels bottom unit, top unit cancels bottom unit here. In this case here, because I know my final answer needs to have moles of acid on top, all I need to do is pick up a divide by 1,000. If it confuses you, just type that part in first, and then you just go divide by your initial volume here of this 10. How I'm going to show it here is multiply by the reciprocal. Divided by 0.0, I'm going to convert to liters, and that's your starting volume of acid, 0.0004. Right? And then we'll get moles over liters, and that will give you your concentration. Ultimately, it boils down to a stoichiometry problem, but I just sort of walk you through how the numbers would look experimentally. So let's just punch our way through. So I'm just going to deal with this number here, 0.0213 multiplied by 0.5 divided by 0.01. The concentration I have is going to be 1.065. And I would need to round that to 3 sig figs because this one here is only 3 sig figs. Because my calculation here is all multiply and divide, when I do propagating errors through multiply and divide, I actually go here 0.0001 divided by 0.0213. So far I'm assuming there's no error on concentration. There's no error from the recipe here. There's an error on the pipette, so let me just add that there. So this is going to be 0.00004 divided by 0.0100. That's the relative error. I'm going to re-multiply this 1.065 to get it back to an absolute. So 1.065 plus or minus 0.0001 divided by 0.0213 plus 0.00004 divided by 0.01 multiplied by 1.065. That's back to absolute. So this is going to be 0.00926. Based on my sig fig rules, I can keep this to 3 sig figs, so I should be able to keep it there. Based on error, I want to round it to 1 sig fig here, so I want to keep this position. So far, I want to say 1.07 plus or minus 0.009. Oh, this doesn't line up here. Usually what we would do is we would say, oh, then let's line it up. Let's go 1.070. Well, we can't because the sig fig rules only let me get up to that position. So in this case here, what I'm down to doing is, even though I could have the precision in third decimal place, let's just knock it back into second decimal place. So 1.07 plus or minus 0.01 is your concentration HCl. Maybe the bottle was initially labeled for you here, oh yeah, it's about 1 molar. Now by doing this titration, I actually know that to a higher precision. I have completely destroyed this sample. So this sample here, I had to count how much H plus with OH minus. I've totally diluted the sample here. But now, because I divided by the initial amount of HCl, I counted how much H plus that the NaOH neutralized with. By dividing the 10 milliliters, I found the concentration was 1.07. And now I know the whole bottle itself is going to be 1.07. Couple last quick notes here. As I mentioned, sometimes your mole ratio is not going to be 1:1. So especially when you're doing your mole ratio at this point here, be careful you have the balance equation. Sometimes, let's say it's a 1:2 ratio, then you're going to factor that in that part there. Also, one other thing here is you'll realize, well, for the one solution, I actually needed to know the concentration. I can only find one unknown given one known concentration. Then the question comes to, well, how do I know the concentration of this one? You could run it through a titration. Maybe I use H2SO4 and then titrate this one. First I find NaOH, but we get into this endless problem. How do I get the starting concentration known really well? There are some chemicals here, this is just some background for you. There are some chemicals that we refer to as primary standards. There's another way we can find an unknown concentration is when I actually make the solution. If a primary standard here, primary standard is typically a solid and is typically very pure, typically very inert, typically doesn't really react. So that if I weigh out a certain, let's say I take, we're going to use KHP in our demo for the next lesson here. KHP is a primary standard, potassium hydrogen phthalate, so that if I weigh out a certain mass, let's say it's 1.00 grams, chemically speaking, because this is so pure, you can leave it out in the atmosphere, it's not going to soak in water, it's not going to react with carbon dioxide or anything like that, it's completely pure. So if you weigh out 1 gram, I'm pretty confident it's going to be 1 gram. You're going to make your solution. Let's say I divide it into, 100 milliliters or so. I'm pretty confident that the 1 was actually this, and I would know the concentration. Let's contrast that with something that's not a primary standard. NaOH is not a primary standard. NaOH, although it also is a solid, although you can also weigh out, let's say, 1 gram of NaOH. NaOH here comes to us as little pellets. Unfortunately here, even if you leave it an hour or so exposed to the atmosphere, you're going to find it's going to very quickly absorb water from the atmosphere. It may actually have some side reactions with the atmosphere particles. This will end up forming an impure sample. You might go through your calculation using the 1 gram, but in fact, even by the time you take 1 gram, dissolve it into, let's say, that same 100 milliliters to make your first solution, it's back to that percent purity question we did up above. I don't really know the concentration of NaOH. So, just introducing to you some of that language there. Where there's only a handful of chemicals. This is an acidic standard. Baking soda is a nice basic standard here. There are certain chemicals that maintain a good purity. You can find the concentration by basically dissolving it, making a solution. And once you have this standard solution, you can use that to standardize and use it in the titration to find other unknown concentrations. You might say here, well, wait a second. We use NaOH here for titration. That's fine. I would have had to find this number by doing, let's use KHP, which is a better standard. Let's first find the NaOH. Once I know the NaOH, then you can use that to find whatever HCl that you need. So tomorrow I'm going to try to pull out a virtual lab for you here so you can see that process here. At least you can see this sort of changing color in action. If you have any questions, just let me know. Thanks, guys.